Hello, so this is going to be a video on taking the derivative of exponential functions. So I know I talked about this a little bit before on a previous video where I talked about e to the x and how it is special, um, but I didn't really get into, I guess, defining the actual derivative. I just kind of threw um, a couple a couple terms and a couple things that kind of hint towards the future. But I hope that this um, kind of seals the deal, I guess, for anything relating to that. So we're just going to start by kind of announcing that a to the x is equal to e to the x ln a. And this is just, you can evaluate this yourself. You could also say that it's equal to e to the ln of a to the x. Really, I'm just taking advantage of these inverses that cancel here, and I took this x out because that's a property of logarithms. Okay, so now that we've established that, I'm going to take the derivatives of both sides, so implicit differentiation, and I'm going to say d over dx of a to the x is equal to equals d over dx of e to the x ln of a, and hopefully you can see that this is a chain rule problem. So I'm going to say that this is equal to, and we're going to employ the chain rule like I said, and it's going to be e to the x ln of a times the derivative of x ln a, and the natural log of a itself is going to be a constant. So we're going to have um, just a, we're just going to have the natural log of a here, because really it's the natural log of a x, and we're considering this as a constant because it is a constant. And when when the derivative applies, this x will disappear. We'll just be left with the constant, like how 2x, the derivative of 2x is just 2. We're just saying that the natural log of x, or natural log of a, is a constant because it is. Because it's a constant base, unlike the variable exponent. Okay, so that being said, e to the x natural log of a we defined earlier as a to the x, so I'm just going to put that right back in, a to the x, and then we have natural log of a. Okay, so this is the derivative, and so it's obviously going to be very useful. You can, I mean, use it in lots of things. It's especially useful in another video I'm going to make probably right after this, where I finally prove to you that E is what makes I guess everything work, and that in this function, in this derivative. You're probably going to want to recap, so if you haven't already, go ahead and watch back the other video I made on exponential functions, where I kind of break down how there's this constant part on one side, and then there's this a to the x um, multiplying into it. And you'll realize that that constant part is this constant right here, this natural logarithm. And I'll get into that in a little bit when I make this video. But for now, I'm going to just give you an example to use this new uh, proof, right? So I'm just going to say, let's say we want to find the derivative of, I don't know, 7x, right? Okay, so we know that the derivative of this, d over dx of 7x, is just going to be, as according to this, is going to be 7x times the natural log of 7. So, I mean, you can evaluate that. I guess I will. Give me a second. Gotta pull out a calculator. Natural log of 7 is 1.95 I'm going to go with. So 1.95 times, well, it's just 1.95. I mean, you don't really need to simplify it then, I guess. Okay. So that's it. That is it, really. So yeah, that's how you take the derivative of exponential functions. So I hope that helped you if you were having questions about that. If you have additional questions, let me know and I'll answer them to the best of my abilities. I am a student. I make these as I go. I don't know everything, so I can also make mistakes from time to time. If I make mistakes, please correct me. I would appreciate it. It's not a nuisance. I really do appreciate it. But yeah, thank you for watching.